Welcome back. And in today's video, we are going to talk about the biomechanics of cartilage. The cartilage is quite known to us. We hear a lot about it in our professional practice. Like the osteoarthritis of knee, we say that the cartilage is destructed and so on. But do you know the biomechanics of cartilage? Do you know that it has some specific properties which give that intact shape and function to the cartilage? Here we are going to discuss about the biomechanics of cartilage. Yes, the biomechanics of cartilage. You know what is cartilage? The cartilage is a hard variety connective tissue. Of course, it is firm but flexible. That's the difference. Not like bone. It's not completely hard like bone, but it's a hard variety connective tissue. But it's a firm and flexible variety of connective tissue in the human body. And of course, we have three different types of cartilage in our human body. That is the articular cartilage, which is also known as hyaline cartilage. The second one, the fibrocartilage, and third one, what is that? The elastic cartilage. Of course, fibrocartilage is seen in intervertebral disc. The elastic cartilage is seen in ears and in larynx and pharynx, etc. And the most important thing is the articular cartilage, which is our topic of interest. That is the articular cartilage, which we see in all the joints around, most of the joint around the human body, the articular cartilage. So articular cartilage is a connective tissue that lines the articulating surface of two opposing bones. So articular cartilage is a connective tissue that lines the articular surface of two opposing bones. And what are the functions of the cartilage? The cartilage generally serves a few functions. One is that it reduces the wear and tear between joint surface, right? Because you have a cartilage, a smooth covering in front of your joint surface, so it is going to reduce the wear and tear of the joint surface. The second one, it helps to transmit the weight between two opposing bones, or it helps in the shift of the load between two opposing bones. You know that from femur to the tibia, the weight is transmitted through the articular cartilage, so it helps in transmission of weight between the articulating surfaces of two bones. And finally, it helps to reduce the contact force. You know that when bone to bone contact is a large amount of contact force would be generated, stress would be generated, force per area. But this articular cartilage, due to its vast coverage, it is actually reducing the force per contact area, or the force that is acting on the unit area in the bone. So these are the three important functions of articular cartilage. It helps to reduce the wear and tear. It helps in the transmission of weight between bones in the joints, and also it protects, or it reduces the joint stress or force that is acting on the bones if there is a direct bone to bone contact. And also it binds together the joint cavity. So that's all about the general aspects of articular cartilage. Now we need to move on the structure of articular cartilage. Right? Structure and composition of articular cartilage. The basic cells in the cartilage is known as chondrocytes. The basic cells that make up the cartilage is known as chondrocytes. So chondrocytes are the chief cells that make up the cartilage. Now if we evaluate further, we see that the human cartilage, or the articular cartilage, often known as the hyaline cartilage, is made up of 70 to 85% of water. 70 to 85% of water. And how many percentage is remaining? 30%. So approximately 30 to 15% is the dry weight. You know that. Okay, this is 100% weight. In that 70 to 80% is formed by the water, and 30% to 15% is the dry weight. right? In this dry weight, the major components are the proteoglycans, PGs, okay? Not postgraduates, but proteoglycans, right? Then collagen, proteoglycans, collagen, lipids, etc. So these are the components of the dry weight of the cartilage. That is the proteoglycans, the collagen, the lipids. So now we are going to discover each and every properties of each of these specific tissues or specific substance that are found in the articular cartilage. So once again, articular cartilage is made up of 70 to 85% of water and 13 to 15% is a dry weight, and that dry weight, proteoglycans, collagen and lipids are the major components. Proteoglycans, okay, proteoglycans. So these are, you know that in every connective tissue there are two type of components. One is the fibrillar component and interfibrillar component. You have the cellular component, fibrillar component and interfibrillar component. And one among this is the proteoglycans. So proteoglycans are interfibrillar components in the connective tissue. Need not remember that. Just remember proteoglycans are interfibrillar components in the connective tissue. Right? Now we have a proteoglycan molecule. As the name suggests, it will have a protein core. Okay? We have a protein core. Right? Along with that, glycosaminoglycan. Proteoglycan is the name. So glycosaminoglycans are being attached. Glycosaminoglycans are attached. So finally we get a structure like a bottle brush. The brush that we are using to clean the bottle. We put it inside the bottle and we clean it up. So we get a structure like a protein brush-like structure. Once again, the proteoglycans are interfibrillar components, and proteoglycans are made up of a protein core plus GAGs, that is glycosaminoglycans. The two GAGs are seen in the cartilage are chondroitin sulfate and dermatin sulfate. You need not remember that. Okay, protein core plus the GAGs. Protein cores plus the GAGs. And the GAGs is attached to the protein core like this. Finally, it makes up a structure which is resembling the the bottle brush that we used to clean. So it will finally give a bottle brush appearance. And when we evaluate further, in our cartilage, we don't see the bottle brush appearance like that. How we see is, we see, for example, you have a glycosaminoglycan and GAG molecule over here. You have another GAG molecule over here, right? The PG molecule over here. Another one, it is over here. And how we see it is, this is usually attached to a backbone. That backbone is made up of hyaluronic acid. It is usually attached to a backbone of hyaluronic acid. Hyaluronic acid. Okay? HU. That is the hyaluronic acid. So how is it attached? In human cartilage, we see that this proteoglycans are attached to a chain of hyaluronic acid. A chain of molecule known as hyaluronic acid, and this exists together. So this exists together in the human cartilage. So what is the arrangement of proteoglycans? The proteoglycans are interfibrillar components, and they are one of the chief components in the dry weight. And the proteoglycans are made up of a protein core. Proteoglycan, protein core. Glycan means glycosaminoglycan. They are seen like a toothbrush appearance, but they are attached to a molecule known as hyaluronic acid. And this finally exists as a unit with about 200 million weight. Oh God, 200 million. No, 200 million Dalton. 200 million Dalton weight, which is very small weight, 200 million Dalton weight. Right? That's all about the proteoglycans. And the proteoglycans occupy now we have the 30% is the dry weight. In this 30, about 30% is occupied by the proteoglycans. So proteoglycans only occupy about 30% of the dry weight of the cartilage. What about the 70%? The 70% of the dry weight of the cartilage is occupied by, can you guess the structure? That is the collagen. Yes, very good. That is occupied by the collagen. The collagen forms about 70% of the dry weight of the cartilage. And the major type of collagen seen is type 2 collagen. We saw that in bone we have type 1. Here we have specifically the type 2 collagen molecules. So this is about the structure, the basic composition of the cartilage molecule. Now, if you want to evaluate the structure of the cartilage molecule, we see that the cartilage molecule is made up of different layers of cell. The structure of the cartilage molecule, let us examine the structure of the cartilage molecule. It is made up of different layers of cell. The first one is the superficial layer or surface layer. The first one, it is the superficial layer or the surface layer. Second one, it is the intermediate layer. Second one, it is the intermediate layer or middle layer. We call it zone also. The superficial zone, the intermediate zone, then deep zone, a deep zone, and finally we have the calcified zone. The calcified zone. So these are the 4 zones of the cartilage. That is the superficial zone or the surface zone. Okay, the intermediate zone or the middle zone, the deep zone, also known as radiate zone, and finally the calcified zone. These are the structure, or this is the form of structure of the cartilage, that is made up of 4 different zones. Now you have to see, if you have a sectional view of the cartilage like this, if you have a lateral view, we see that initially we have the superficial layer, okay, then just below that superficial layer we have the another layer, that is the intermediate layer. Then next to the intermediate layer we have the deep layer, and next to the deep layer we have the calcified layer. So this will be how it is arranged. And finally this calcified layer is attached to the subchondral bone. The calcified layer attaches the cartilage to the subchondral bone. Subchondral means just below the chondro. Chondro means cartilage, okay? Subchondral bone, alright? So that is the general structure of the articular cartilage, which I would like to mention once again. That is made up of a superficial layer or surface zone, the intermediate zone or middle zone, the deep zone or radiate zone, and finally a calcified zone. The calcified zone is the lowermost part and it is attached to the subchondral bone. The superficial one, of course, is the topmost or the superficial zone of the cartilage. That's all about the brief structural specification of the cartilage, where we saw in biomechanics of cartilage, we had an introduction about the cartilage, then about the composition of the cartilage and structure of the cartilage. Why the structure is important? The pathophysiology. The recent study says that in osteoarthritis, there is a loss of these layers of cartilage. There is an appearance of few fissures in the layers. Fissures means few gaps in the layers. There is fibrillation of different layers, and even there is a complete removal of layers of articular cartilage. So that is a recent discovery in the field of osteoarthritis treatment, and it has a great scope of development too. So that comes of pathophysiology. So if this has been asked somewhere, you can write after this the pathophysiology in osteoarthritis. The different layers of cartilage are washed out or go for fibrillation or fissures. Fissures. Fissures are seen inside the layer, which weakens the bone, which weakens the cartilage. It's a classical sign of the cartilage osteoarthritis. Alright, and now we move on to the Mechanical properties of articular cartilage. The mechanical properties of articular cartilage. Alright. The mechanical properties of articular cartilage can be the mechanical property of articular cartilage and the modeling of articular cartilage. Okay. The mechanical properties of articular cartilage is as a sum of all the different substance that makes the articular cartilage. Right? What are the substances that making the articular cartilage? We already discussed the proteoglycans, the collagen, the lipids, and the water. So the sum of all the properties of this, the sum of the properties of all the constituents, all the components of the articular cartilage gives its a unique mechanical property. So the mechanical property of a cartilage is not a property of either collagen or proteoglycan, but it is a combined property of all the components that are seen in the articular cartilage, right? And now we see the proteoglycans, the proteoglycans, when they are in an aqueous environment or a watery environment. You know that there is a synovial fluid, and we also saw that 70% of the cartilage is made up of water. Exhibit or shows a charged property, that is, they act as an anion. Okay, anionic charge. They shows an anionic charge, that is a negative charge. So this shows an anionic charge. So the proteoglycans in an aqueous environment or in a watery environment shows an anionic charge. Right? Now you imagine, let us take for example, this is an articular cartilage session, and you have 1, 2, 3, 4, 5, 6 anionic charged proteoglycan. What is the property that we studied in our physics classes? Like charges repel each other. So this will repel each other, right? So this won't allow the articular cartilage to come together. It will always create some repulsive forces in between. Okay? Now you imagine this articular cartilage. Inside the articular cartilage, the proteoglycan molecules are free like this. Your proteoglycan molecules are free like this. It can move here and there. So already there is a friction force, so it can move freely over here. It can occupy entire this white space. What? The proteoglycan molecule. But to avoid that, in the cartilage, we have a specific arrangement. There is a collagen molecules. There is an interdisposed collagen molecules, and in between that you have this proteoglycan molecule. Now you see the motion of the proteoglycan molecule is restricted. It is in the meshwork of collagen. It can only move in between that. And now here comes the biomechanical property or the significance of this unique charged proteoglycan. See, now we are applying some compressive force to the cartilage. Okay, it won't go for a complete deformation. Why? When it goes for some amount of deformation, already the negative charged ions will produce a repulsive force. The negative charged ions will produce a repulsive force. See? And that will not allow a complete deformation or an extreme change of the shape of the articular cartilage. Or in other terms, it always produces a compressive force. It always produces a force inside the articular cartilage, which is very good for our body, which is very good for the preservation of articular cartilage. So in the structure of the articular cartilage, in the mechanical property of the articular cartilage, the mechanical properties are regulated by all the components inside the articular cartilage. And one of that component is the proteoglycan. And what is the peculiarity of the proteoglycan? The proteoglycan molecules are seen as negative charged inside the water. But if they are free to move around, they can create a lot of problem. They can occupy a lot of space. But we don't want to do that. The body don't want to do that. So it is confined into a extracellular matrix or a matrix of collagen. So it cannot move here and there. It can move only in that matrix. And now when there is a pressure applied, when there is a deformation of the articular cartilage, the deformation is limited because The deformation is limited because the negative charged ions will repel each other and will produce a repulsive force inside the articular cartilage. So that is one of the features of the mechanical property of the articular cartilage. The second mechanical property is due to the water content in the fluid content or water content in the cartilage. You know that when there is deformation, what happens when there is deformation? If there is a water molecule in between this both hands, when I'm deforming it, it can move here and there. So this, during the application of deformation, the movement of the fluid also regulate the cartilage function. The movement of the fluid also regulate the cartilage function, right? Once again, when there is a deformation, the fluid inside the articular cartilage can move freely here and there. It can move freely here and there. And that is why we say that the property of the articular cartilage is sometimes like that of a fluid. So the articular cartilage, we saw that it is having properties of what? It is having properties of proteoglycan. Now we studied that it is also having properties of water. So together, this act like a sponge, right? It act like a sponge, but a sponge not allowing water to pass easily, okay? It act like a sponge. What the articular cartilage or the cartilage inside the human body act like a sponge. And that property, the mechanical properties of the articular cartilage, is a sum of the property of the deformation as well as the fluid movement. And thus we have a model of articular cartilage. Thus we say, or thus we developed a model of articular cartilage that is known as biphasic model of articular cartilage. Biphasic model. Biphasic model of articular cartilage. This is the most relevant model, the biphasic model of articular cartilage, which says that the mechanical property of the articular cartilage is a sum of property of the solid components, which are the proteoglycans and other components, as well as the fluid. The mechanical property, the biphasic model is a model which states that the mechanical property of an articular cartilage is a sum of the solid phase as well as the properties of fluid. That is, it is a sum of deformation. It is a sum of deformation and fluid movement and fluid motion. So the articular cartilage property, mechanical property, is a sum of the deformation and fluid movement inside a articular cartilage. So it is a sum of fluid movement and the deformation inside an articular cartilage. The deformation is produced by the solid component for making the solid phase of articular cartilage. Solid phase of articular cartilage, or solid phase or solid component. Which are the solid component? They are the proteoglycans, they are the collagen, they are the elastin, they are the lipids, etc. And then you have the solid phase and the fluid space, which is made up of the interstitial fluid and water inside the articular cartilage. So we finally arrive at a conclusion that the mechanical properties of articular cartilage is actually a sum of property of the fluid component and the solid component inside the articular cartilage. So when there is a compressive force that acts on, the solid component becomes tight and tough. Along with that, the fluid component also becomes tight and tough to produce the constant, rigid or firm appearance for the cartilage. Thus, fluid components inside the cartilage, when the pressure is applied, cannot move free. That is because there is in fact a sudden movement as well as there is an extracellular matrix of collagen. And the proteoglycan molecules can attract the water molecules also. So this is what we have about the general picture of our cartilage. And in next session we will be discussing about the material properties of articular cartilage, which includes viscoelastic property, that's a Poisson's ratio, Then we see about the permeability of the articular cartilage, which is a new term because articular cartilage contains a lot of fluid. So the permeability of the articular cartilage, we will be discussing that in the next session. So to wind up this session, let us once again see the articular cartilage. The cartilage is of three types, and one among that is our articular cartilage. And articular cartilage is the cartilage, is a firm and flexible cartilage that lines the joint surfaces in that lines the bone surfaces in joints. And articular cartilage has three different functions. We studied about that functions. Then we went on to see the structure, the composition of the articular cartilage. Chondrocytes are the cells that makes up the articular cartilage, right? And then we saw about the different type of components inside the articular cartilage, the proteoglycans, the lipids, the collagen, etc. We saw that the proteoglycans are seen like a bottle brush appearance, and attached to a hyaluronic acid they forms a molecule. The collagen is type 2 collagen and occupies 70% of the dry weight of the articular cartilage. And then we saw on to the structure of articular cartilage, where it is made up of 4 different zones: the superficial zone, the intermediate zone, the deep zone, and the radiate or the calcified zone. The calcified zone. And finally, we went on to the pathophysiology, and then we jumped on to the mechanical properties, where we saw that we have a biphasic model of articular cartilage design, and which states that the mechanical property is a sum of fluid and solid components of the articular cartilage. Yes, that's all about today's session. And if you like the video, please don't forget to click the like button, and don't forget at all to subscribe to our channel to be updated with all the latest development in our channel. Next session, we will be discussing the part 2 of the biomechanics of articular cartilage.